And again, when we do have the quiz, please turn your videos on. I have to see you while you're taking quizzes and tests. All right, so you can turn them on now, but certainly you need to turn them on later. And again, please let me know, remind me if your video is not fixed yet. Again, that has to be done pretty quickly. You need to have those videos completely fixed. I would say by next week, because we have another test next week. All right. So I think next Thursday, not this Thursday, but next Thursday will be the second test. All right. So let's get to PowerPoints.
Next Thursday's the test.
Uh-huh. All right. So I think this is where we left off last time here. We were talking about the relationship between two variables, where we would, let's just go back a little bit here. We would have like suicide rate on the y-axis, prestige rating on the x-axis. And we would have these xy points that we plot just like we did in algebra. And then we would calculate what's called the correlation, L, which is the strength and direction of this relationship, this quantitative relationship. So again, the correlation runs from -1 to 1. The -1 is perfect negative correlation. +1 is perfect positive correlation. 0 means no correlation. And by the way, correlation only measures linear relationships, as a straight line. It does not measure nonlinear relationships. So if you see a nonlinear relationship, correlation is not useful for that. You don't apply it in that case, right? So in the final exam, if they give you a curved type relationship, say that correlation is not applicable. It only applies when we see something that looks like a straight line, like this one here. Okay? This is negative correlation here, right? It's trending down. And if you drew a line that went through these points, these points would be very close to the line. Therefore, the correlation is very close to -1. The negative indicates downward sloping, and the number indicates very strong negative correlation. Right? Any correlations near -1 or +1 means strong correlation. So the question is, how do we specify the relationship? We use what's called regression. It's a procedure to draw a line that's best fitting. There's many lines that could go through, let's say, look at this one here. Many lines that we could draw through these points. There's one that's best fitting, which means that the distance from these points to the line is the closest, all right? It's the closest distance to the line. And you don't have to worry about the mechanics of how the regression line is created, because it uses calculus. Anybody who's taking calculus, it's very easy. It's a very easy thing to figure out. But most of you probably have not taken calculus, so don't worry about it. The equation of the line of best fit looks very familiar to you, hopefully. Y is equal. Now they use A and B instead of M and B, but if you remember in high school, it was Y is equal to MX plus B. Here they say Y is equal to A plus BX. It doesn't matter because the number that's multiplying the X is your slope. And the other number that's being added in is the y-intercept. Y-intercept is that point where the line intersects the y-axis. Right? The slope tells you how much y is increasing for a 1 unit increase in x. All of you have taken this. This should be familiar, but if you haven't been in high school for a while, maybe you forgot about it. But in today's high school, you have 2 years of this, where this is repeated over and over and over again. So it should be pretty ingrained in your memory about this equation. All right. So let's assume that you know this equation coming into this course. For example, here, this is a scatter plot of, and this is called a scatter plot, by the way, when we're comparing two quantitative variables. And it's comparing the age of a wife and the age of a husband for some British husbands and wives. And the equation is 3.6 plus 0.97x. Now, what does that mean? That means that, now notice x here is the age of the wife. That's the x-axis, and the age of the husband is the y. So what the slope is telling you is that for every year that the wife's age increases, the husband age increases by 0.97 of a year. That's what the slope means. 3.6 says, and it doesn't make any sense. You know, you have to understand that the y-intercept is just there to draw the line and where it might intersect the y-axis, but sometimes it doesn't mean anything, because in this case here, it's saying when the wife's age is 0, the husband's age is 3.6. All right. Well, husbands and wives don't get married, right? I mean, certainly when the wife is born, she doesn't get married, right? When x is 0, that means you're born. And so, you know, your husband's not going to be 3.6 years old, you know, when you get married. So in this case, the y-intercept has has a silly interpretation, but it's there to complete the equation so that you can make predictions. Now, what kind of predictions can you make? Well, you can say something like, all right, suppose the wife is 20 years old. What's the predicted age of the husband? Well, if you replace the x, which is the wife's age, with 20, and multiply it by 0.97 and add 0.36, down here you can see the calculation. The predicted age of the husband is 23 years. All right. So why do we want to do this? Well, suppose in our data set here, we do not have a wife that's 20 years old, and we want to predict how old the husband would be if the wife is 20 years old. Well, we're going to use our equation to make that prediction. We simply replace the x with the wife's, and then do the arithmetic, and you come up with 23 as the estimated age of the husband. So, and by the way, in high school, if you've just been in high school, maybe a couple of years ago, you've seen this before. This is now part of the Algebra 2 curriculum. Right? This is high school math we're talking about here. It's not even college math. This is high school math to make this sort of prediction. Now, in high school, everybody has the TI-83 or 84 calculator, at least most high schools do. And so you're taught how to come up with this equation using that calculator. And in this course, we don't have that. We don't have that calculator. We're not using it unless you happen to have one. So what do we use? We're going to use Microsoft Excel. So I'll show you in a minute an example of that. Now, this slide here is saying that when we make our predictions, we don't want to pick a value of x that is outside the range of the x's that are in your data set. Because the range of x's that are in your data set pretty much determine that line. But it's possible that outside that range, that means x's that are smaller than what's in the data set, or x's that are bigger than what's in the data set. It's possible this line may not be the right line for those numbers. So this word extrapolation means we don't use values of x that are outside the range where the data falls, all right? And if we do want to make a prediction based on that, we really can't. That's the point. We can only make a prediction for x's that fall within the range of the x's in the data set. All right. And then they have an example here, which we're not going to go into because I think, well, it's a little complicated. So yeah, it's a little complicated. I'm not going to go do this as an example. I'm going to show you an example with Microsoft Excel. By the way, here are the formulas, which look very ominous, don't they? They look terrible. They look awful formulas for calculating the correlation. This correlation coefficient requires all these calculations here. And then to get the slope and y-intercept of the regression line requires also these calculations, right? So all of this here, if you're a math person, maybe you would be interested in this, but if you're not, you would certainly shy away from this page. So what I'm going to do now is show you an example of doing this sort of thing in Microsoft Excel, right? Now, for those of you who don't know Microsoft Excel, there are YouTube videos out there which tell you how to use it, all right? So You should learn how to use it, by the way. You should learn how to use it. Why? Because um, almost every business that's out there requires it, and you know it. All right. So you want to learn, work in the business world. Wrong here. See. All right, hold on 1 second. I don't know what the issue is here. See what's wrong with my Microsoft Excel. Oh, I see. There we go. All right. All right. So let's get back to that. Sure. Should be able to see it now. All right. For those of you who've done some things in Microsoft Excel, this should look somewhat familiar with the spreadsheet. It has rows down this way and then columns running this way. Right? So when we refer to a particular cell, these little boxes in here are cells, it has a row and column. For example, this word Anchorage is in row 4, column B, so it's B4. That's how it's referred to as B4, that position here. And the number next to it, 55, is in C4. And then we have this number, 56.1, is in D10. All right, so that's how it's done. It's a spreadsheet, Now, again, if you're not familiar with this, it's very easy to learn, at least the beginning. You don't have to be an expert with Excel to be able to do the things that I'm showing you here. All right, you just have to become familiar with how to use it and how to enter data. Entering data is very easy. It's not hard to do. But again, a YouTube video, just as an elementary introduction, and maybe I'll find one and I'll post it in case you're having trouble finding one, but there's probably thousands of videos on that you can Google that will teach you how to, do what I'm showing you here. All right, so what the data is here is there are 3, 6, there's 8 cities in the United States. A couple of them are in, one of them is in Alaska, that's Anchorage. These other are in mainland US. And what we're doing is we're looking in a particular year, we're looking at temperatures, the average temperatures in Fahrenheit in June and in December. Now the June temperatures are considered the X, or independent variables. Independent variable. What does that mean? That means that we're using these temperatures to predict the December temperature. All right. So this is the X. So if we plot this on in a scatter plot, the X-axis will be the June temperatures, and the Y-axis will be the December temperature. So we're using X to predict Y. All right. Using the June temperatures to predict the December temperatures. Now, here are the actual average temperatures for these cities in December of that year. All right, so they just average all the temperatures for all the days in December, average all the temperatures for all the days in June, came up with these numbers. And then what we want to do is we want to see if there's any correlation between these. Now, we would possibly think so, but we'd actually have to calculate it. So how do we do that? Now, in this column here, in column F, I type in the word correlation. You can actually type in anything you want. I type in the word correlation with a colon next to it. And right next to it, I have what's called a formula. A formula is always start with equal sign. So you're going to type in an equal sign in this cell here. And then you type in the function. This is a function, CORREL. Guess what that stands for? Correlation, right? Correlation. So you just type it in. Now, if you didn't know it was CORREL, you could start typing in equal and then start typing in the word correlation. And all of a sudden, like if I do it here, and I type in equal, and then type in C, and immediately it starts giving me possible functions, and then O, and then R, and there it is. Right? So I just double click it, and it gives me a parenthesis, and it opens up, and it says array 1 and array 2 with a comma in between. What's an array? It's just a list of numbers. A list of numbers. So array 1. Now, in this when we do correlation and when we do the regression line, we typically want to put our y variable in first. So if I want to if I want, this array is referring to a column. So if I want to put my Ys in, my December temperatures in first, what I do is I simply highlight, I just click one of these and then run my cursor all the way down. I just click and hold, and I'll run it all the way down, let go, and then put a comma. And then I do the X's next, and I just click the X's, first one in the X's, and just scroll down, holding the left key when I'm doing that. And then I close the parentheses. And then hit enter. And that's where I got my, this is what I did here. All right, I just showed you how I did it up here. The correlation, equal sign before the function, and then there's a parentheses, and then you have your Y's first, so you scroll with the Y's, and then you hit comma, and you scroll the X's, and then close the parentheses and enter, and you get your answer. Right? Again, if you're not familiar with this, what I just did, again, a little introductory video on how to use Excel will show you how to do this. Now, the question, of course, is, you might say, is where did I get all this data from? Well, I entered it. This was a problem in the book, and I simply typed in the information that I saw, and in this format. That's all. I typed in the names right here, like Anchorage. I just typed in the names, right? And then I typed in, and then I put city above it. Now I highlighted it. You don't have to highlight it like I did, but I just typed in the word city because that is these are the cities. And then I typed in June for June temperatures, and I typed in December for December temperatures. And I just simply enter these numbers one at a time. I enter a number and then hit enter, and it'll typically scroll down, and I hit another one, all the way down to the last one. The same thing for December. So it's very easy. It's not a hard thing to do. Now, this particular spreadsheet, by the way, I have, now I think, if I'm not mistaken, I might have to, it's already posted, but I might have to repost it because I did change a couple things in here. So I have to double check. So don't wait about a day, wait till tomorrow before you download this onto your laptop, this Excel file. Now down here, by the way, is I put 75 here because I'm using this as my prediction. All right, so in this cell here, I'm using Philadelphia as another city, and I want to predict if in Philadelphia, if it's 75 degrees in June on average, what would be the predicted temperature in December? That's what I'm trying to figure out. All right, now what I'm going to use is this so-called regression line, the line that best fits this data. How do I find that? Well, the y-intercept of that regression line, I go down this column here. Notice I have equal, and I have the word intercept. So the word intercept, according to Excel, is the y-intercept for that regression line. And then it'll open up a set of parentheses, and once again, I put my y's in first. That's D4 to D11, and comma, we put our x's in C4 to C11. Close the parentheses, hit enter, and we get negative 38.967. Excel calculates that for you without knowing calculus. You don't have to know calculus. You simply type this in, and Excel gives you the answer. The slope equals slope. So the function here is slope, and do the same thing, and you get your slope. That's how I got this equation here. This, by the way, is just I simply typed in this. All right, I typed it in. Show the equation, but you don't have to do that. And the y-intercept is given, the slope is given. And then you just plug in into the equation to get your equation. And then what this little line here is, or this cell here does, is it takes that equation. And how does it do it? It says, all right, G11. G11 is what? My slope. I multiply by my x, which is right here, C14. That's my x. My slope times my x plus the y-intercept plus what? G10. Which G10? The y-intercept's right here. Will give me the predicted y when x is 75. X is 75 degrees in June in Philadelphia. Predicted y, the temperature in December, average temperature in December, according to this equation, should be 39.8 degrees Fahrenheit. All right. Now, I will post this for you. These formulas are here. The only thing that you would have to change if you're going to do any of this would be is the actual data. All right, it will be a different data set I'm going to give you with what may not be temperatures. It may be something else, but there'll be two columns. All right, two columns with data. One is the X. The first one's the X. The second one's the Y. You may have to insert some rows, right? How do you insert a row? You just highlight the row and then you go to insert up here. And where is it? Where's the inserting the row? Maybe it's not there. Let's look at, here it is. You go to home, insert. If I want to insert a row, I can do that. All right. It says you can insert cells, but you can also insert a row. Insert rows here. So if I click that, I just added an extra row between here and here. So that's how you would add more data, is that you can insert a row, right? And then when you do your formulas, make sure you include all of those values included in the additional rows that you've added, with the data in them. All right, and that's how you do regression with Excel. It's very easy. Once you learn how to do all of this, it's just point and click, and you got your answers. It's nothing. Any questions about that? So the questions that I can ask you for this type of, for chapter 10, in terms of math, are three questions. Number one, I can ask you for the correlation. I can ask you for the equation, and I ask you to do a prediction. And by the way, that's high school. That's high school math. That's exactly what you do in algebra when you have this type of situation, this regression line. In algebra 2, that's exactly what they ask for: correlation, the equation, and the prediction. That's it. Those three things. And this spreadsheet does it all for you. You don't have to do anything else. All right. That's it. There's no reason you should get any of this wrong. As long as you know how to do this stuff in Excel, as long as you know how to do it. In other words, you know how to change these numbers here to something else, to another data set. As long as you know how to do that, you should be good. All right. And if others of you have worked with Excel before, this is very easy. This will be like a piece of cake for you. But for those of you who haven't, you're going to have to learn a little bit about how to use Excel, and then you'll be able to do these problems very easily. All right. So that is chapter 10. Look at now chapter 11. Chapter 11 is just continuation of this idea about relationships, about that it can be deceiving. All right, so this is just some information about this. It says, look at the two pictures to speculate on what influence outliers are having on correlation. Now, for the correlation, look at the first picture here. Remember, correlation measures the strength and direction, right? Strength and direction. And here is an outlier over here, one up here, right? Now the rest of the dots are pretty close to each other. So number one, do you think that the direction of the correlation is changed at all by having that dot there? Do you think the direction is changed? It's sloping up to the right for the other dots. Is that dot going to change the direction at all?
No.
No, no. Do you think it's going to change the slope of the line?
No.
Well, it would, because this dot here will pull the slope up. All right, slope, because the line of best fit has to include this point here. So it's going to pull the slope up. But as far as correlation is concerned, do you think it's going to weaken the correlation or strengthen it, this dot here?
Neither.
Remember, go ahead, I'm sorry.
Like it wouldn't change the correlation really, right? Because it's
It,
just
it will no, it will change the correlation by a lot. But I'm
um,
asking you, is it going to weaken it or strengthen it?
strengthen it.
All right. Now think about what I mean by correlation. Correlation measures how close the dots are to the line. The closer the dots are to the line, the stronger the correlation. So if we have a dot that's up here, what does that do to the correlation?
Oh yeah, weakens.
Weakens it. That's exactly right. It weakens the correlation. Okay. So we would expect it still would be positive because this dot here is moving. It's still in the positive direction, but the slope's it's gonna slope up. But because it's going to slope up, these dots down here are going to be further away from the line, and this dot's still also going to be far away from the line. We're going to see a significant decrease in the correlation because of this dot here. If we remove the dot, this is very strong correlation. How about this one here? Do you think this dot affects the correlation?
I feel like not as much because it's like in the same direction as the other dots.
Well, not
Like
only the direction, it's you could picture a line going through these dots and continuing to be close to this dot also. In other words, it's continuing the line that you could picture going through the other points. So this should not affect the correlation by very much. It could strengthen it, could weaken it, but not by much, because you could picture a line going through here and then actually going close to this point too. So not much of a change in correlation with this dot, with this outlier, but certainly with this one, we would see a weakening of the correlation because the line is going to be pulled up and away from these points because of this dot here. Here, the line should not change at all. Pretty much. Should be pretty much the same line. Okay, so that's good. That's a good one to look at. Now, correlation has been found in a certain city in the Northeast U.S. between weekly sales of hot chocolate and weekly sales of facial tissues. You think that hot chocolate causes people to need facial tissues? Use your common sense. What's your common sense tell you?
Too late.
No.
No, of course not, right? Yet we can see correlations between these two. Why? Because it could be the winter time. There could be another variable that's influencing both these, right? We call that confounding variable, right? Wintertime, it could be cold outside. People drink hot chocolate, people's nose run. If we're colds or something during the wintertime. You see what I'm saying? So a strong correlation does not imply one variable is causing the other. It could be that one variable causes the other, but in this case, it seems silly, right? That hot chocolate causes people to need facial tissues, unless people use the facial tissues to wipe off the hot chocolate off their face. Doesn't make sense, but but you see the point? Here's the idea. Correlation does not imply causation. Another way of saying that is correlation means there could be there could be a relationship there, but it may not be a causal relationship. It could be another variable causing both of them to occur in the same direction. Okay? That's a very important point. If we were to draw a scatter plot of the number of women in the workforce versus the number of Christmas trees sold in the United States each year between 1930 and the present, you would find a very strong correlation. You think one thing causes the other? You think there's causation here? Number of women in the workforce versus number of Christmas trees sold. Is one thing causing the other? Common
No.
sense?
No, it doesn't.
Of course not, right? But why would you think it could happen that these things increase at the same time? Well, this is kind of, to be honest with you, this is an old textbook. So it's a little bit biased, gender biased. You could call this gender bias. The reason really is that in the past, let's talk about 50 years ago, 60 years ago, during Christmas time, more women who were homemakers back then. Maybe your mom was a homemaker, who knows? But back then, women were homemakers, men were out working. Not that way now, but they went to they for extra money, women went into the workforce to work in department stores, things like that, for temporary jobs during Christmas season. And so Christmas season, you would see an increase in women in the workforce, and at the same time, obviously, Christmas trees were being sold. So that scatter plot would show a strong correlation, but definitely not a causal thing, because what's causing this in the past was Christmas time. Christmas time in the past had more women work, and at the same time, Christmas trees were being sold. All right. Here's the thing that we talked about earlier with with those outliers. Outliers can substantially increase. Inflate means increase, or deflate, which means decrease correlations. Also, groups combined can mask relationships. That's something that's interesting. That's something that a lot of professional researchers kind of forget about the idea of this masking because of groups. But we'll show you an example of that in a minute. All right, an outlier that is consistent with the trend of the rest of the data will increase the correlation, inflate it. So that example we saw before, if we go back to it, This one here, you would think maybe an increase in the correlation, maybe an increase, possible. That's what they're talking about there, the first example here. And then an outlier that is not consistent with the rest of the data can substantially decrease the correlation. And that was that first case here, this one right here. It certainly is not consistent with the other ones. So we expect a significant decrease in correlation, certainly for that one. All right, so that's what they're talking about here. Now, outliers sometimes indicate errors are made in the data set. That's what they mean by data points are corrupted. They initially recorded, or when they're entered in the computer, there could be some errors there. So if you see an outlier, one of the first things you should check for, see if there's an error. That's what they're referring to here. Okay. Here's a data. So here's two quantitative variables. You're dealing with the speed limit as the independent variable, the x, and the death rate per 100 million vehicle miles along the y-axis. That's your dependent variable. You're plotting these as XY points for these various countries, and you see Britain over here and Italy over here. This correlation between if you include all these points, the correlation is 0.55. 0.55 is considered a moderate correlation, not really strong, but not really weak, but it's positive. Picture a positively sloped line going through these points. If Italy's removed, correlation drops to almost 0.098. Why? Because if Italy's removed, there's no clear upward or downward trend here, is there? All right, you can picture almost a horizontal flat line being the best line that fits this data. And it's just slightly positive, but 0.098 is close to 0. That is called pretty much extremely weak correlation, practically 0. Now Britain is removed. Now all of a sudden you could picture a line going upward sloping more strongly. As the correlation jumps to 0.70. So you've removed Britain here, then all of a sudden these points you could see the upward slope more, and that's why the correlation goes up. Right? So this is a good example of how different points can influence your correlation, making it go up or go down, depending on how far away it would be from a line. Now, ages of husbands and wives. Here's again here are most of the points, but here's an outlier standing all the way up here. It's an outlier here. Okay. Here's an example where the wife is very young and the husband's very old. Right? This is like a 22-year-old wife and a husband who looks like in their 80s. Now, you might look at it and say, wait a minute. Maybe in Hollywood, we might, or somebody, you know, a situation where you're dealing with a billionaire or something, maybe you would see a marriage like that. But most likely this is an error. So you check it out and you say, oh, the person entering this entered a 82 instead of a 28. All right. So that error, what did that error do? Because this data set point is all the way up here, that error dragged the correlation down to 0.39. But then if we remove that outlier, all right, the correlation of the remaining points is 0.964. Very, very strong linear relationship, positive linear relationship, very close to 1. And you can see it, right, with the rest of them here. But if this was 28, right, if this is supposed to be 28, the point should be down here somewhere. And if we included it with the correction, we would have seen probably not 0.964, but probably 0.9, 0.85, something like that. It's still a strong positive linear relationship. So it's very important to check these outliers to make sure they're not mistakes. In this case, it was a mistake. And that mistake caused the correlation to be much smaller than it should be. All right. The outliers can be legitimate data, or it may be mistakes. All right. All right. Look at this one here. Here is earthquake data, where the magnitude of the earthquake is the independent variable, the x variable, and the number of deaths is the y variable. And here are some cities where there was major earthquakes. Okay. Notice it looks like it's trending down, which is interesting, right? In other words, you would kind of scratch your head a little bit here, right? You'd say, wait a minute. If you consider all the data, it's saying that the stronger the earthquake, the fewer the deaths. That makes no sense, right? Right. And actually, it's a very strong negative correlation if you consider these points here. But there's one point all the way up here. What is that point there? What's that point? That's an earthquake that occurred where? San Francisco earthquake. There's that. 1989. Okay, big earthquake, and many deaths. All right, big earthquake, many deaths. So that's this one right here. I think that's the one they're referring to. That's the one from 1906. Excuse me. San Francisco had 2 major earthquakes in the past over 100 years. 1989, and then there's one 1906. That's the one 8.3. That's the biggest earthquake. I think that might be one of the largest ones the U.S. has ever had. And there were 503 deaths. So this is an outlier here. This outlier, by the way, is causing the correlation to be 0.689, so a pretty strong positive correlation. But if we remove it, we see actually a negative correlation. But anyway, that outlier is making that correlation positive when, and that if we remove it, it would be a negative correlation. Notice the direction of the correlation change because it's not just the magnitude of it, the direction of the line of best fit change. Okay? You have to be careful when you present it. And again, here's what I said earlier: legitimate correlation does not imply causation. It could be silly things that seem to be correlated with each other, as I showed you previously. And especially if it's an observational study, we cannot control for those other variables, what are called, what are they called? Confounding variables. So we cannot prove causation. There could be causation, but we can't prove it. Correlation does not imply causation. And this is an example of that. Now, so you go look through those examples and go through the chapter. Some reasons that you may have relationships between variables. It's possible that the explanatory variable is the direct cause of the response variable. It is possible. Because we say it does not imply causation, correlation, it does not imply causation, doesn't mean there isn't a direct cause. It could be a direct cause. Possible that the response variable is causing a change in the explanatory variable. In other words, the cause could be reversed. It's possible. That's possible too. That could be causing the correlation. The explanatory variable is a contributing but not the sole cause of the response variable. In other words, there could be multiple variables that are causing the change in the response variable. Confounding variables may exist. Yes, of course. Both variables may result from a common cause. Remember the Christmas example with the ladies working more during Christmas and the Christmas trees. That's an example of that. Both variables are changing over time in the same way. So time could be the variable that's influencing both variables. It's just both variables tend to increase or decrease together over time. Or, and this is always a possibility, the association may be nothing more than coincidence. It just could be a coincidence. That's possible too. So here are the 7 possible reasons you could see correlation. We're getting close. We have 5 more minutes for our quiz. Okay. All right. Now, these are just examples of those 7 examples, things that we were just talking about. Confounding variables may exist. Here's 4, 5, and 6, I think. Confounding variables related to the explanatory variable and affects the response variable. All right. That could explain why there's correlation between the explanatory variable and the response variable. Because there's a third variable there, the confounding variable, that is related to the explanatory variable and is also affecting the response variable. Both variables may come from a common cause. Again, the Christmas tree example. That was a possibility. Again, they give more examples in here of all these the same thing. We could go through them, but we're running out of time. Here's possible that both variables are changing over time. Here's 2 variables that we have: the divorce rate and percentage admitted for drug offenses. All right, we're seeing the divorce rate increasing over time. We see the percentage admitted to drug offenses increasing over time. Is one causing the other? Not necessarily. Possible, but not necessarily. But simply, the correlation between these 2 variables could be because they just happen to be increasing over time. That's all. The time could be the reason why the variables tend to be correlated. Okay, we see a lot of that actually in statistics. There's a lot of examples where time is the reason for the correlation more than anything else. And then coincidences, right? All right, a new building, here's an example here. A new building opens up, and within a year, there's an unusually high rate of brain cancer among the workers in the buildings. All right. Suppose the odds of having that many cases in a building is 1 in 10,000. All right. But there are thousands of new office buildings. All right. Thousands of new office buildings. So should we expect to see this phenomenon just by chance in about 1 of every 10,000 buildings? Yeah, it's possible that we could run into a new building that by coincidence just happens to have a high rate of brain cancer. All right. It just could be a coincidence. That's the whole point of it. All right. And again, this whole idea is causation. How do we determine causation? Randomized experiments. Okay? Randomly assigning people to treatments, then we can talk about causation. All right? That's how we confirm causation, through a randomized experiment. All right? Okay. Any questions about that? All right, let's stop sharing. And I believe, if I'm not mistaken, it's getting close to that time, 2 minutes away. Any questions about anything we covered in this today? So what will be covered on Thursday is going to be chapter 12. Now, chapter 12 has to be all by itself because there are some calculations in there that are a little bit on the complicated side. I have to admit, that will be for some of you a little challenge. It'll be something called risk, which is probability based, but it's going to use tables, and we're going to calculate things like odds and things like that. It may get a little complicated. So we're just going to be working on chapter 12, and I will show you an example of how to do those calculations. I mean, and it's all also posted. It'll be a PDF of how to do those. So, but make sure that you review on your own chapter 12 when you leave the meeting on Thursday. Make sure you go over that, and you may have to go over it 2 or 3 times before you understand it. So it's a little bit more complicated, just giving you a heads up about that. All right. Then we have another quiz, which on Thursday, which will cover chapters 9 and 10. Now you may ask, well, how about chapters 11 and 12 that we're covering today and on Thursday? There will be another quiz next Tuesday, which is the day that we do a review for test number 3. So we have 3 consecutive days with
So
quizzes.
7 and 8 is today, right?
7 and 8 today, 9 and 10 Thursday, and then 11 and 12 on Tuesday, next Tuesday, when we have our review. All right, so that's basically it. It's 8:50 now, so check your Canvas. Give a thumbs up if you see the quiz. Yes, good. All right, great. So go ahead and I'll put myself on mute and stop the video. I'll stop the recording also. If you have any